Welcome to the very first explainer in our journey through calculus. Now, before we actually start calculating the dynamic motion of the entire universe, we've got to understand the bedrock tool that makes it all possible, and that is the function. You see, calculus is literally the mathematics of change in motion, and the function? Well, it's the exact tool we use to describe that change.
Just think about a ticking clock, right? Or the rapid growth of the world's population, or even the sudden, violent rumble of an earthquake. These aren't just random, disconnected events. They're shifting, changing quantities. Our world is in constant motion, all the time. And to actually predict and understand all this motion, we need a very specific mathematical language to link one changing quantity to another.
The renowned mathematician James Stewart actually talks about this in his textbook. He describes capturing this dynamic change as beautiful, calling calculus one of the greatest achievements of the human intellect. And honestly, I totally agree. But to actually appreciate that beauty and, do the actual math, we need a highly disciplined tool to represent these relationships.
And that fundamental tool is the function. At its core, a function is simply a rule. It links every element in one set of numbers, which we call the domain, to exactly one element in another set, which we call the range. Think of the domain as your starting point and the range as your destination. But here is the absolute golden rule: exactly one element. One starting point simply cannot lead to two different destinations. That strictness, that's exactly what makes it so reliable.
It actually helps tremendously to visualize a function like a machine. Picture it. You have an input, which we usually call x. You drop that x right into the machine. Let's call the machine f. The machine churns, it processes that number according to a very specific pre-programmed rule, and then, boom, exactly one result pops out on the other side. We call that single output f of x. One input goes in, one strict output comes out.
Now, how does this actually play out in practice? Well, James Stewart emphasizes something called the rule of 4. This basically means we can translate our mathematical machine into 4 distinct languages: verbally, numerically, visually, and algebraically. And the true skill here, the real mark of mastering calculus, is being able to seamlessly shift back and forth between these 4 representations.
First up, we can describe a function verbally, just using everyday words. For instance, the temperature of the water depends on how long the water has been running. We all know this from turning on the shower in the morning, right? The temperature, our output, is directly tied to the time elapsed, our input. So yes, that is a perfectly valid function described entirely in plain English.
Second, we can look at a function numerically using a simple table of values. Take a look at the human population of the world at different times over a century. The year is our input, and the total population in millions is our output. Now, sure, this doesn't give us a neat little formula, but it gives us hard, concrete data points showing exactly how population depends on time.
Third, we can represent a function algebraically with an explicit formula. Honestly, this is what most people picture when they hear the word math. For example, the area of a circle equals pi times the radius squared. You drop the radius into this algebraic machine, and it calculates exactly one area perfectly. It's compact, it's precise, and it lets us do incredibly complex calculations with just a few symbols.
Finally, and perhaps most importantly for how our human brains actually work, we can represent a function visually as a graph. This is often the absolute best way to understand a function's behavior because it brilliantly illustrates the overall trend of the data. You don't just see a single point, you get the complete life history of the function at a single glance. You see exactly where it rises, falls, peaks, and bottoms out. To see how this perfectly applies to the real world, let's look at the devastating 1994 Northridge earthquake in Los Angeles. When the ground literally starts violently shaking, scientists don't exactly have the luxury of neat algebraic formulas to describe what's happening beneath their feet, right? Instead, they rely on seismographs. These instruments produce a graph where the ground's acceleration is recorded as a function of time. By graphing this visually, a geologist doesn't need to write out some massive, complex algebraic equation. They can instantly read everything they need to know: the massive amplitudes, the dangerous patterns, the duration of the worst shaking. The visual graph tells the entire story of the earthquake in an instant.
But this brings us to a really crucial litmus test. If a visual graph is our ultimate decoder ring for understanding the real world, how do we actually know if a shape we draw on a piece of paper is a valid mathematical function? Remember our strict rule from earlier: one input must yield exactly one output. So, is every squiggly line you can draw on a coordinate plane a function? Well, the answer is a hard no.
To test this, mathematicians use something incredibly simple, called the vertical line test. Here's how it works. If you take a vertical line and sweep it right across your graph, it must never touch the curve in more than one place. If it intersects twice, well, that means one input is giving you two different outputs. It totally breaks the fundamental rule of our machine, meaning it instantly ceases to be a function.
So now that we know what a function actually is, that strict, reliable machine of inputs and outputs, how do we use it to predict the future? How do we use these functions to build actual mathematical models of our changing world? Well, in our next explainer, we are going to dive deeper into those exact questions and start applying this practically. So, if you're ready to see how deep this rabbit hole goes, join us for the next session. See you then.